Hello everyone, welcome to Triaright, the new era of learning. This is Pack 365 in Module 6. Today we're going to learn about model evolution methods in machine learning. Let's begin the topic. Model evolution methods. Model evolution in machine learning involves assigning a model's performing and its ability to generalize to unseen data. This process relies on various methods and matrices which differs depending whether the task is classification, regression, or another type of machine learning problem. So here the what the slide can say it like this. So in this topic, in the definition, we can say that so it is a model evolution methods. It gives a general introduction to okay. So expanding the model evolution in machine learning. So we can say that it generalizing the performance, so it has the expanding, specifically focusing on the supervised learning. Here an explanation of main concepts. Okay, so the supervised learning is a type of machine learning where a model is trained on a labeled data, right? So we can say that the goal is to learn a mapping from input features or output labels to determine how well a supervised model has learned this mapping. We need to evaluate this performance. The fundamental principle of model evolution in supervised learning is to test the models on a data it has no seen during training. This is a typical done by the splitting the available data sets into the parts. Okay, so it has a training sets and validation sets on development and test sets. So we have most of the evolution parts. Two types of supervised learning here we can learn. So let's take the simple steps with what is machine learning. So we all know that machine learning is a starting set we called as bot. Okay, that we want to train the machine to gain the knowledge and information about the models and the algorithms and the concepts. Okay, so it's a data analytics techniques that provides a system with the ability to automatically learns and improve from the experience without the being on especially programmed. So they learn on simple data to make the predictions or decisions in the future data, right? So what is good for machine learning models, right? What task is the model designed to perform, and how can we access whether a model is doing it well? How would you evaluate human performance like that? So according to we use NLP, right? Here we have neural networks too to understand the what's the data set running in the analysis part or the identify the patterns like that. So there is a no one type of model that definitely solve any problem. Neither is there any one set of definitive set of the data that produce a best predictions. So we have various models, right? Let's begin to discuss that models. So first we have model evolution. So carefully analyzing the model's outputs to evaluate whether they are meeting the goals that we set up for it. Okay. So this is will allow us to compare the models. So underfitting, overfitting like that. So here we can carefully analyzing a model output to determine it meets to goal the set for it. Okay. Compression in different models. So this also includes a diagram that visualizing and representing the three common scenarios in this model. Okay. So what's that fitting, which are the crucial for understanding the model evolution, like underfitting, overfitting, and approximate fitting, right? So approximate fitting means the diagram shows the scatter points. The diagram which shows the scatter points here. So we show the scatter points, scatter plot of the data points, scatter plot of the data point. Okay. So the line which we can see that the black line was the plotting of scatter data points. So which two different classes represented by the red and blue dots. The goal and classification model is to learn the distant boundaries that accurately separate those two classes. Okay. So it is that. So when it comes to underfitting, like comes to overfitting again. So here we can see that overfitting and green line. We see the green line here. So representing a model that is too complex and has learned to the training data too well. The curved green line is highly flexible and the perfectly separated all the training data points. Okay, it even captured the noisy and the random the training sets. Okay, so like that we can call as. So here we can see that we have another So it's called we in this underfitting, right? Underfitting in pink straight line. So pink straight line is, this represents the model that is too simple capture that underlying the patterns in the data. The straight pink line attempts to separate the red and blue points. Okay, but it clearly misclassifying any many points of the both classes. So it prevents the overfitting. We split the data we have and some to train the model and some to test the model. So split data methods like how we would hold on is train validation test data sets. Okay. So another we use cross validation like k-fold cross validation. So holdout testing. So here we can say holdout testing of it. So data is divided into train validation test set, right? And split it usually 60 20 20 like that. We see in here in k-fold method, right? In previous lecture we see in the k-fold method is proper. So, but if we have a lot of data, it's enough to test in a smaller proportions, right? So, like like we can say that 10 lakhs, we can say that here the data of 98 by 1 and splitting, and as long as high confidentially overall performance, right? Validation of the test should be comes from the same distribution, something that reflect the future data, right? So, another key point we have model learned from the test data, test validation that performs it's not enough, and we did not another round test performance it good enough that we test on the test data, right? So it's like studying from an exam, like study practice test refocus studying repeat final exam. So like we have here, so what's the method of holding testing, right? The core concept of the holding testing is to participate or reversing the portions that the data set of the evaluation model performing the unseen data, right? So this method helps to access like how well we model generalize to new the real world data and the critical steps in identifying issues in the overfitting. Okay. So it has a various method like data splitting. We have validation sets, we have test sets and split ratios, and we have data distributions from. So try testing workflow. The model is trained and tested at a time. So the model performs the test in the validation set. So based on the good validations, we can say that good enough. So we have to test the little least data. So half of the data we are going to training, half of the data we are making the test at a time same time. So again, we have cross-validation test. So it's also same data, but dividing the data into k number of sets, like we have the k-fold. So cross-validation testing means we use a k-fold. So leave one set of the testing and try on k minus one. That repeats the combination of the sets, the compute of the average in each test, right? So here what we're doing is we have the alt a number of iterations, like we have the data types. So first state we start from here. So here we're trying the like take we have the 80% data, 100% data. So here we're trying the 20% and remaining 80% will be use the training fit. Okay. So after the next fold, this test data comes into the training. Okay, this test data of the all those test data comes into training, right? Comes into training, and this test data comes into again this those here we can see the right. Wait, I draw you and show you. So we can see we are dividing this graph. Okay, we are dividing here. So we are dividing this. So here we have the 80%, right? This all data set which must be 80%. So this data may be 80%, right? And this test data will be 20%, right? So for first test data which has it comes into the training, right? The data comes into train. For the where first training data, you here to here which is the training data in first iteration. So it comes into the test. So same steps repeat until all the data sets get trained and test okay at a time. So it's a cross validation. So here we have model matrix and two. So in model matrix, we can say that it is a way of quantifying how well a model performing the certain. Okay. So different two types of model need different types of matrix. It it's like score of an exam. The score each prediction has right or wrong, and to produce the overall score the of the model. We can give more importance to a type of performance, like the we can give more value to the certain questions on the exams. So here we get the model matrix or the numerical measurement that quantify how well as a machine learning model is performing on a specific task that provides an objective way to compare the different models, like track progress in during training and determining the model and good enough for the applications. Like we have quantifying performance, task specific metrics, analogy, and assigning. So this overall the diagram. Neural diagram at the bottom of the slide appears to show that several figures holding a piece of paper, right? Several people holding a piece of paper with a different symbols. So check mark of X, like that check mark of X, and a circle with a star. This likely represent the visual metaphor for the different predictions being made by the model. The figure all telling up those are results come up for the final score, which is represented by the light bulb of a star on the top. So each and every has one idea. Here we can say that each and every has a different data sets and they have a different idea. So this was represented the model matrix. So overall, it is the why the specific method and matrix discuss the overall the matrix like tools allows to conduct the model evaluations. It choose which tool is used to depend on the entire problem. Like the most important thing, we have the classification model. Predict a class for interpreted. Class for each inputs. Binary classification. It is a picture of a cat or not. So it is a classification method we most use in the machine learning concepts. Okay. So here we have multi-cats, like we have a multi-class. If a picture is a cat, a dog, or an owl, so we classify that. So multi-label objects in pictures is a cat or an animal or black. So output is commonly the probability of an input belonging to the class, which can change the decision threshold. So we can say that if the cat is or it analyzes the eyes, nose, ears, legs, and tail, each and every analyzes and it gives a final conclusion as it is a cat. In the next picture we see this animal, so we can analyze the we have not a proper shape of it has a shape, but in face it has enriched like the other animals. So like this, it decline the it is not a cat. So like the classification works done in most of the classification done in the neural networks. So here we can say that. So classification model evolution. We tend to use accuracy, right? How many right predictions we got overall predictions made. So this does not work well for the imbalanced problems. For example, a fraud detection algorithm that predicts all the transactions to be valid, right? If we have 5% of fraud transaction, the accuracy is 95, but the model is useless. So we can say that the classification model is more is used in email spam and fraud calls and fraud alerts. It will be generate. So it valid and it checks where the mail is. It checks the sentence of the each every mail text, right? Then it analyzes and classifies the to be fraud mail. It is just purely consented to the forward mail. So then it can be slide to be proper mail. So confusion matrix, it was one of the model prediction reality. So versus reality. So we have the predict like we have positive, negative, and true positive. Like we have true negative and we have false negative and false positive, right? So it is actual box. So let's disclose it. So in it we have one common precision and recall. So precision of the positive prediction, how many we are actually positive. Recall is nothing but recall of all the actual positive results. How many did the model predict were the positive? So precaution, like precision and recall are the matrix derived from the confusion matrix. Okay, and they provide a view of the model's performance of simple accuracy, particularly useful for understanding a type of the error or model. Okay, so this clear in defining the precision, the slide of all the positive prediction, how known as actually. So it is a formula we call as precision formula here, true positive plus false positive. Overall, we have the overall total of true positives and true false, right? How many get the positive and negative in those? It takes the true positive and recalls the same. It has a true positive and true false negative and true positive. So it actual formula discloses like that. Okay. So for recall, the recall measures the model ability to find all the positive instance for data set. A high recall score means the model is good at finding the most of or all of the positive cases. It answers the question of all the actual instance, how the many model successfully find, right? So actually, the confusion model has two positive. Like we can say that when it comes to the open, like I will see a simple term. So we can say that if we have true positive, so TP, the model correctly predicts a positive instant. Like okay, the model predicts correctly. So like example, if a person is fever with or sick, the person is correctly is in a sick, like that we can say that. So false positive. False positive means the model incorrectly predicted a positive instance. Like we don't have a particular data set to prove it's true, but it has predicted as a it has a some health issue. So like that, false positive. And false, we have false negative. So overall false negative means the model is incorrectly predicted a negative instance, like or properly predicted the negative instance. And true negative. True negative is nothing but the model is correctly predicted the and overall the depends on the correct positive decisions. Let's here I have example of 100 transactions, 5% or fraud, right? So we have the 100% transactions and we have 5% of frauds. So model one, all transactions are detected as fraud. So the actual transaction is true positive is 5 and false positive. Like we don't have like how we have false positive 95 because we have estimation like we have the fraud. Like okay, all transactions are detected as a fraud. Like we have detected the all transaction as a fraud, but not in a just it's detected, but not concluded as particularly we detected. So it has a false true. True positive is it declares a 5% or get fraud. So it declares a true false, true positive. Like some of the fraud is must be done. So like that, according to the condition, it declares the its cause. So only one transaction is correctly defected as a fraud. So true positive is it fixed only correct defected has a one fraud. So it has a true positive is one and false positive zero and the true negative is 95. So according to that, this table bit works. So here we have F1 score. So we want to compromise on the precision and the recall. We use the harmonic mean because punishes extreme values. We can adjust the important. We can give each of them in a critical system model. We many want to favor recall has a to not miss any positive results, right? F1 equal to 2 into into recall plus precision plus call. So here what the we can say we can break like say that the F1 score is a harmonic mean of a recall and recall. Sorry, precision and recall. It is a single composite matrix that uses to widely use it in evaluate the classification model, especially in the situation where imbalanced data sets. It provides a more accurate reflection of a model performance that accurates alone. Okay. So compression and prediction recall. F1 score is a when we want to compromise on the precision and recall, as we have discussed the those two matrices are often in opposition. A model can achieve very high precision at the cost of low recall, or vice versa. The F1 is seeks to combination of those single matrix to reward the model perform well on the both. So it shows the prescription versus recall. Trade-off has the very threshold to identify the positive in a out model. So approximately for the imbalanced data sets. So here we have some of the view like recall. So receiver operating characteristic curves to show how the true positive rate, one false positive rate here. So true positive rate recall and false positive rate probably of a false alarm. Better the balanced. So it shows the threshold in the classification model that outputs as probably logistic regression and the model prediction that probably an email being spam or addition threshold is used classifying the instant. For example, probability of spam is a greater than 5%, 5% or 50% we can take. We classify it as spam. Otherwise, the classification is not spam. Like the curve is generated by the calculating of the true positive rate and the false positive rate and a various threshold value of the 0 to 1, like it transfer. So here what we get the TRP and FRP like. So how we get generate a formula here. So we can generate a formula like here. So if the value of TRP, if the TRP formula means we can say that. So here we have the TRP. So TRP formula is TP by so true positive we have and we can say true positive plus false positive, false negative. We have the two for true positive and is the equation false negative. For FRP for false positive rate for false positive rate we have the formula has false positive by again this false positive and true negative. We have the true negative as a formula. I hope you understand this equation. Okay. So here comparing models, we can quantify the model curve by calculating the total area of under curve. So AUC summarize the skill of the model across the threshold. The F score summarize the model skill as a specific threshold and regression model. So the model targets the prediction values the given in the previous value, house price prediction and stock price prediction. So we have the underfitting, approximate fixed rate, overfitting. So training and testing the methods are the same, but different, but differs it how we assess this model, how we assess those models, how we use this model, where we use those models in a particular data sets. Okay. So regression matrix. So we have the mean absolute error and the mean squared error, and we have the MSE mean squared error. Penalize a large error means that MAE, right? Mean as a absolute error. So where the data sets divide according to dividing, and where is mean absolute error, and where the mean square error, it detects in regression matrix. So we have the clustering models, and we have the unsupervised learning. We don't have a labeled data, right? We don't have labeled data with a ground truth. So we use a matrix that measures the how self-similar observation or the same clusters. Does not really measure the validity of the predictions, but it can help the comparing the models. We go into the clustering. So overall conclusion. So we get it very important to understand what model does what we want to measure, right? We want to learn what model which can predict which model can help in the what situation we was. So one matrix does not fit it all. Okay, it is no. So matrices are only useful if you can compare them to something. So be careful when testing your models. You may be overfitting. So this is the overall conclusion of this evaluation model. Okay. So I hope you guys all are understand about this topic. Thank you.